we are starting our first module with a discussion of some fundamental concepts. And our topic is thermodynamics. And thermodynamics is the study of heat energy and its transformation. And as you know, heat is a form of energy, and there are some methods by which you can convert this heat energy into work or chemical energy, etc. And we are discussing these things in our coming classes. And this transformation is governed by certain laws called the laws of thermodynamics. And the laws of thermodynamics are also familiar to you from your higher secondary classes and your chemistry complementary classes. And as you know, we have 4 laws in thermodynamics: the zeroth law, first law, second law, and then third law. And actually we have 4 laws, and we are starting from the zero. And the reason is that we have introduced a law and gave it the name first law. And then only we have introduced a law which should be more fundamental than the first law. So that should be before the first law, and before the number 1 we have the number 0. That is why we gave the name as the zeroth law. And you do not confuse with the idea that the zeroth is name of a particular person. Zeroth means it is a number 0. So the zeroth law, first law, second law, and the third law. And in this unit, we will discuss the zeroth law. In the coming unit, first law. And in our third unit, we will discuss the second law with the discussion of heat engines. And then third. So, as an initial stage, we have to discuss a term known as thermodynamic system or simply system. And since we are discussing a system for thermodynamics, we are calling it as a thermodynamic system. And the coming topics, when we are just mentioning the term system, it means that it is the thermodynamic system. And this term is also familiar to you. And a system means a finite portion of matter or restricted region of space which is set aside and on which our attention is focused is called a thermodynamic system. So, if we want, we can consider our classroom as thermodynamic system. So, if our interest is, or if we want to study the whole property of this classroom, we will consider this room as a thermodynamic system. Suppose we want to study the properties of half portion of our class. So, that half portion is our thermodynamic system. And if the whole ground floor of our block has to be studied, so that whole ground block is a thermodynamic system. That's all. And everything outside the system and which has a direct bearing on the behavior of the system, you can call as the surroundings. So, when you are considering this classroom as the system, the outside things are surroundings. And when you consider only half portion of this class, the other half portion is the surroundings of this system. And there is a separation between the system and the surroundings. And the separation you are calling as the boundary or partition or wall. And from our example itself, we can clear that the boundary can be of 2 types. And they are either real or imaginary. We have mentioned that if the half portion of our classroom is taken as the system, there is no physical separation between the 2 portions of the classroom. So, there the boundary is imaginary. But if you are considering our classroom, there is a wall, brick wall or wall made up of stone. it is surrounding our classroom and it is a real boundary. And through this boundary, there can be exchange of matter or energy. That means either matter or energy or both. That means energy as well as matter can be transferred between system and surroundings. And in physics, we are always interested in the transfer of energy alone. And in chemistry, chemical thermodynamics, always you will discuss with the transfer of mass as well as energy. And this term universe is also familiar to us. The system and surroundings is commonly termed as the term universe. So universe equal to system plus surroundings. And here you can see that this is a system and so you have the surroundings, and there is a separation between system and the surroundings that we have marked as the boundary. And now we are classifying our system based on the transfer of matter. One way is based on the transfer of matter. So the first one is closed system. If no matter crosses the boundary, the system is said to be closed. In a closed system, energy can be transferred through the boundary. No problem for that. With respect to mass, no mass can enter the system from surroundings, or no matter can leave the system to surroundings through the wall. Such a one is a closed system. And an example we are mentioning pressure cooker or a gas confined in a piston and a cylinder. If you consider the pressure cooker, you can see that it is tightly closed, and suppose that weight of the pressure cooker is also tight, you can see that no matter can, or that means either gas or liquid, whatever may be, it cannot go inside the cooker or from cooker to outside. But you can heat that pressure cooker by putting it on or by placing it on a flame. So there is a possibility of energy transfer but no mass transfer. Such a system is a closed system. And the other one is open system. Here you can have the exchange of matter and energy. As an example, if you boil some water in a vessel, open vessel, you can see that when it is boiling, the water vapor can escape from the vessel to surroundings. So such a thing is known as an open system. So based on the transfer of matter, we have classified the systems as closed system and open system. And now based on the transfer of energy, the classifications are adiabatic system. In an adiabatic system, it does not exchange energy with the surroundings. And we have mentioned this, that means interaction between system and surroundings is possible through work. This concept we will discuss later. So simply an adiabatic system does not exchange energy with the surroundings. And an isolated system means no transfer of mass or energy. That means no interaction between system and surroundings. So these are the classifications, and in this figure you can see it. You have isolated system, adiabatic system, closed system and open system. This red dot shows mass. So in an isolated system, no transfer of mass or energy. In adiabatic system, no transfer of mass and energy. In closed system, transfer of mass is not possible, but only energy. And in an open system, both can be transferred. So if you compare this isolated system and adiabatic system, you can see that no possibility of entering of mass and energy. But the difference is that an isolated system is completely or purely isolated. It will not have any interaction with the surroundings. But in an adiabatic system, this system can interact through the surroundings by the performance of work. That means, if this system, say, it is expanding, no mass is actually entering into the system or leaving the system, but you may consider it as a balloon. When it is heated, that balloon will expand. Or sometimes it is expanding, and when it is expanding, we can see that system is performing work on the surroundings. So such type of interaction is possible in an adiabatic system, but such interaction is not permitted in isolated system. And also we are classifying the boundary, that means the separation between system and surroundings, as diathermic and adiabatic. Through a diathermic wall, energy can be exchanged between system and surroundings. Example of our utensils or a vessel. When you are placing it on a flame, you can see that through the vessel, heat can enter the water, enter the system, or enter water to boil it. That means that vessel is allowing the passage of energy, and such a wall or boundary or partition is known as the diathermic boundary. And no transfer of energy between system and surroundings is possible through adiabatic wall. As an example, we can consider our flask or thermos flask. If you are putting something inside that thermos flask, it kept that thing as hot, which means that no heat energy can leave that system to outside. So that boundary or partition between the system and surroundings of that thermos flask is preventing the transfer of heat energy. So that thermos flask is an example for adiabatic boundary. And while you are drawing figures, you have systems A and B. You can see that a single line is drawn between A and B, and a double wall is drawn, and this is a single wall. Always this adiabatic wall is represented by double walls by diagonal shading. So this is an adiabatic wall. That means surrounding A and B, you have an adiabatic wall. That means no transfer of energy. And between this A and B, a single line or a heavy line, and through this energy transfer is possible.